Hey everyone, in this video we're going to talk about Lab 4. And so first in Lab 4 we're going to investigate the Thevenin equivalent circuit. So first start the Simulink, create a model, and we start by saving the model. Okay, MATLAB 225, and I'm gonna name it Lab 4, the first one, Thevenin 001. Alright, and so first we want to create figure 3, right? So we need to bring in some components. So first go to library browser and then Simscape, electrical, and in the passive elements we're gonna need the resistor, add that, and a voltage source from the sources. From the sensors we're gonna need the current sensor and a voltage sensor and the electrical reference. So let's close the electrical, and in utilities the PS to Simulink converter and the solver configuration. Let's close the Simscape and go to Simulink, and in sync add a scope. So all the components appear on top of each other. So let's take them apart. And right, so let's first create the circuit shown in figure 3. So we need a couple of resistors here, another one on top here, Control R to rotate, another one here. Okay, and this goes here. Okay, so let's connect these up. Oops. Okay, so this is 1.2 kilo ohms. Let's put in the values. This is K 1.2 kilo ohms. This is 1 kilo. This is 470 ohms. And this one on top is 4.7 K. And the voltage source is 1 volt AC with the AC peak amplitude is 1 volt, and the AC voltage frequency is 1000 hertz, 1 kilohertz. Okay, so this is the circuit shown in figure 3. Now we want to calculate the open circuit voltage and the short circuit current across these two terminals. So we're going to need two circuits here. So I'm just going to copy and paste this like so, and measure the voltage here. So Control I to flip. So I'm going to measure the voltage on this circuit, and the short circuit current, Control R to rotate on this circuit. Okay, so this is going to give me the open circuit voltage here, and this is going to give me the short circuit current. So because the frequency is 1000 hertz, I can just reduce this to 0.02, and because I don't need 10 seconds, 0.02 should be enough. And run this. So let's open the scope for the voltage. And so if you go to the signal statistics, you'll find that the peak amplitude or the maximum amplitude of the voltage is 0.441, which is what we calculated in the pre-lab. So our calculations were correct. And for the short circuit current, if you come here and then go to signal statistics again, and you'll see 0.423 milliamperes here. And then if you divide that open circuit voltage divided by this short circuit current, you should get the same resistance, the Thevenin resistance that you calculated in the pre-lab. Yeah. I'm going to name it Thevenin 2. And since we are working with the same original model as before, I'm going to bring this model, copy and paste it basically to my new model. Now I want to connect this as build the circuit shown in figure 6, which I only need a resistor and a capacitor connected to terminals X and Y. So Control R, and I can bring the capacitor from the library browser. So in here, Simscape, electrical, passive, capacitor, and then add it. Control R. Okay. So let's connect everything up. Okay, so this should be 1 kilo ohm, which it is, and this should be 0.047 microfarad. Okay. Okay, so I'm going to need to want to connect the same load to the equivalent resistance model. So I'll need basically a voltage source and a resistor for my equivalent resistance model. So delete this. So this is going to be my V Thevenin, and my V Thevenin from pre-lab was 0.441 volts, and the resistance was 1041 ohms. Change this to ohms, and let's connect these up too. Okay, so since this is the equivalent resistance of this part, I expect, and I'm connecting the same load to both of these, I expect that, oops, I forgot this part. I expect that the voltage I see in these two scopes to be the same. So let's run this, and oops. Okay, so let's, we don't need this 10 seconds, so let's change this to 0.02 and run it. Okay, so here you'll see that the voltage, the max value of this peak value of your AC voltage here is 0.213, and let's look at this one. So, and in your equivalent circuit you have the same thing, so 213 again. So you'll have, you can see that you have the same voltages. And change this to 4 kilohertz and then run the simulation again, and you'll see that you'll have the same results in the voltage of these two scopes. So yeah, 0.187 here and 0.187 here too, and because this is just resistors and the equivalent resistance, so it wouldn't matter what frequency you have here. Next, we're going to investigate the notch filter shown in your pre-lab. So I'm just going to copy this and then bring it into a new model, and then modify it to create the notch filter, which is shown in figure 8. Okay, so don't need these. You need a voltage source at the input and a voltage source at the output. Okay, and I'll also need an inductor, which I can bring from the library Simscape electrical passive inductor and add it from here. Okay, rotate, then I'll bring it here to connect it to my capacitor, and then let's connect everything up. Okay, so now we want to plot both these voltages in one scope, so right click on the scope and then signals and ports, number of ports 2. So like this. Okay, the resistance here is 820 ohms. The capacitor is 0.047 microfarad, which is correct, and the inductor is 0.1 Henry. Okay, and the voltage, change the AC peak amplitude to 1 volt and the frequency to be the notch filter with the notch frequency, which is 2322 hertz based on the pre-lab. Okay, so first let's save this to notch. Okay, at first when we run this, because it's at the notch frequency, we expect the V out to be 0 because the impedances of the inductor and the capacitors cancels out, so you're left with a 0 volts across these two terminals. So let's simulate this circuit and see how it behaves. So for the total time, we don't need 10 seconds. Just 0.02 should be enough, or 0.01. Okay, save and run. Oh, before that, let's name these. So this is V out, and then double click on this arrow to name it V in. So let's run this again. Okay, so this is okay. So you'll see this that the blue waveform here is the input voltage and the yellow waveform here is the output voltage. There is a transient part for the output at the beginning, which we don't care about in this course. And then, as you see, after a transient, it settles down to a steady waveform, which is the steady state operation. In ENGG225, we care about the steady state operation. So let's just we have to zoom in here to see our waveforms. So the blue waveform is the input and the yellow is the output, and as you can see, yellow is trending towards 0. So if I change this to V out, you'll see that the maximum value of that AC is about, it's very small. But in order to get even a more accurate result, you can just go here and go to the modeling. So and follow the steps shown in the lab instruction in figure 5 to set up the solver configuration for physical models. So this is one way to get a better result for our case. Go to model settings, and then in here choose type fixed step. Open this solver details here, and in the fixed step size, change this to 10 micro, sorry. So 10 micro, okay, and then run the simulation again. You'll see that now if we zoom into the steady state, this V out is really close to 0. And you can see it here as well by the numerical values. Okay, so next step, you need to graph the amplitude of the output voltage versus frequency. So for example, in frequency of the notch frequency, which is 2322 hertz, your peak amplitude, you can find it from here, 0.45 times 10 to the power of minus 4 and volts. So this is basically 0. So you have 0 volts here at this frequency. So let's change the frequency, for example, to 1 kilohertz here and see how that how my AC output would change, would behave. So in 1 kilohertz, so again I'm going to zoom in here. Okay, so the blue is the input and the yellow is the output. You'll see that in 1 kilohertz my AC peak would be 9.58 times 10 to the power of minus 0.98 volts basically. And that's another point on the graph that you need to do. You need to make. So you need to make a graph that is between 10 hertz to 10 kilohertz, and you just perform these tests and collect this AC peak amplitude of the output voltage for each frequency, and then connect those dots to complete your plot. And the points that you need to collect the data samples from are given in your lab instructions as well. So let's just do another one here really quickly. So for example, 10 hertz, right? So we wanted 10 hertz. And so this is a special one I'm doing good, because in 10 hertz, if you have 0.01 simulation, you can't see the actual peak, right? So you didn't give it enough time to show you this simulation, the sinusoidal waveform. So you need to change this to a higher value. 0.2 would be enough here. So if you run this again, you'll see that V in and V out are almost on top of each other. So the same, so V out, the maximum value here is 1 volts. And yeah, so I'll repeat this for different frequencies and then collect the amplitude of the output voltage and connect those samples to complete that graph. So next we're going to create the low-pass filter circuit that we did in the pre-lab. So let's just copy this and then paste it in a new model, new blank model. Okay, so right, so I don't need this inductor in the RC filter. Disconnect this capacitor, and my capacitor is 0.047 microfarad, which it is. The resistor we found in the pre-lab to be 9,960 ohms, 9,960 ohms, and the input voltage is 1 volt, and the frequency is the cutoff frequency, which was 350 hertz. We want it to be 350 hertz to see what our output voltage is. Okay, so if we have 1 volt here at the cutoff frequency, we expect to see 1 divided by root square of 2. The peak amplitude should be 1 divided by root square of 2 at the output. Okay, so let's change the stop time here to be 0.02 and save this model. ENGG225 low pass. Let's call it low pass. lab4 low pass. Okay, now, okay, I'm gonna go to the model and my model settings to change the solver selection to fixed type to have a better result. So, this was 10 micro, and okay. So run this and okay, open this up. So V out is the yellow line here, and as you can see at the beginning here we have a kind of an overshoot, not an overshoot, just a little bit higher peak than we have as the other ones, and this is the transient part again, which we don't care about. So make sure to always zoom into the steady state part where things are repeating themselves. And in that, let's look at the maximum of the V out, and you'll see it's 0.0 0.707, which is exactly what we expect at cutoff frequency, which is the peak amplitude of the input, which is 1 volts divided by the root square of 2. Okay, so we modeled our low-pass filter, and we saw that the resistor we found in the pre-lab actually corresponds to that corner frequency that we wanted. So next, we want to draw the diagram of the amplitude of the output voltage, same way that we did in the previous part, versus the frequency. Okay, so to do that, we're going to need to collect different samples at different times, at different frequencies. So for example, let's take a sample at 500 Hertz instead of 340 and run the simulation again. Okay, open this up. And again, at the first we have this transient which we don't want, so always make sure to zoom into the steady state part where things are repeating themselves, and you'll see that the peak amplitude here is 0. So always make sure of this E. So this is 10 to the power of -1. So this is 0.56 volts, and so this is another point. So at frequency of 500 Hertz, your maximum, the amplitude of the output voltage is 0.56. So you can repeat this for different frequencies. We've given you the frequencies that you need to repeat this in order to get a good enough graph between 10 Hertz and 5 kilohertz, 10 kilohertz. So let's just look at the frequencies below. So for example, at 150 Hertz, if you want to go below the cutoff frequency, make sure to change this stop time to a higher value. Oops. Okay. So let's change this to 0.1 because your frequency is lower right now. And then you'll see that it's coming up. Okay, for example, at 150 Hertz, zoom into the last part and you'll see that this maximum is the amplitude, would be 0.9 volts. And yeah. Okay, and then repeat these for different frequencies, find different amplitudes, and complete the graph. Thank you very much, everyone.